Rector of LPL, and I'm really happy to welcome all of you here tonight, both here in person and those of you that are joining us online. The LPL, as you may have seen from the earlier slides, has a long history in lunar exploration. We One of the first big projects here was the effort to create what was called the Rectify Lunar Atlas. And when you go out tonight onto the right, you can see a really beautiful print from that, where the telescopes around Tucson were used to create high resolution images that we then reprojected using kind of analog old school techniques to see what the moon would look like if you were orbiting it like an astronaut looking down on the moon. And the original Lunar Atlas helped NASA plan for the first lunar missions, and our founding director Gerard Kuiper played a big part in the Ranger missions to the moon to photograph the moon and make maps of the moon. So we've been in the business of studying the moon for a long time, and as I like to say, the first L in LPL is lunar for our role in studying the moon. The Our lecture series this fall, every fall we have a lecture series, and the theme this year has been on the moon because NASA is in the process of sending humans back to the moon for the first time in over 50 years. The You may have during Apollo, NASA flew a number of seeds, tree seeds. I think it was on Apollo 14, which orbited the moon, and those seeds were then planted. Saplings were given to different institutions across the country, and some of those trees are still alive today, including our own moon tree, which is between our building and the Flandre Planetarium next door. And in honor of that original idea of taking seeds to the moon, putting the moon and bringing them back, NASA did the same thing again on the Artemis 1 mission, which orbited the moon. And again, seeds were planted. They brought the seeds came back. They were planted, and just a couple of weeks ago, we planted a sapling, a sweet gum tree, on the north side of Flandre, which is now only about this high. So now we have two moon trees, and I like that because it's kind of looking back in the history of the role we played in Apollo, and also looking forward to the role we're going to be playing in returning humans to the moon with the Artemis program. And that tonight, to conclude our series on exploring the moon, we're going to hear from research professor Angela Marusiak, who uh, joined joined us here at LPL back in 2023. Angela received her bachelor's degree from Boston University in 2013 and her PhD from the University of Maryland in 2020. And she's a real expert on seismology of planets. Her thesis title was Planetary Seismology Using Single Station and Small Aperture Arrays, Implication for Mars and Ocean Worlds. And I think that's one of the exciting things going forward is using the modern day instruments to study the interiors of worlds and what's happening on the inside, whether it's the moon, Mars, even asteroids or the icy bodies. Angela was a team collaborator on the InSight science team, which landed the seismometers on which is a seismometer on Mars. She's a science team associate for the Dragonfly mission, and she's a member of the science team for LIMS, which is the lunar seismology package we'll be hearing about tonight. She's published dozens of papers about the seismology of planets in our solar system, and I'm excited to welcome here tonight. So please welcome Dr. Angela Marusiak.
So first of all, can folks hear me?
Yes.
Yes. Okay, awesome. So I'm really excited tonight to be talking about Artemis and how we're going to be exploring the moon to come and continuing on LPL's legacy of lunar exploration. So just so folks know what the next 40-ish minutes will look like, I'll do a little bit of a background on seismology. That way we're all sort of caught up to speed and on the same page with what I'm talking about. And I'll also be talking about some planetary exploration that we've already done. And then where we're going. So Artemis science goals, why are we going back to the moon 50 years later? And then I'll also touch upon what LPL is doing for Artemis and SciSLIMS in particular. here at LPL. So humans have been interested in seismology since essentially the dawn of time. Anyone who has experienced an earthquake probably knows they're quite startling. So you probably want to figure out, why exactly are they happening? So there's been records that since the first century BCE, we started really studying earthquakes. And in about 132 CE, the Han Dynasty actually came up with a seismoscope. So there's a replica of what that looks like here. The way the seismoscope worked is when the ground would shake, a ball would drop out of a dragon's mouth into the mouth of a toad. So this couldn't tell you how strong the ground was shaking, what magnitude it was, but it could tell you which direction it came from, cool. Which was really useful because for the large emperor, they could be able to send out folks in, the direction of the ball and basically figure out where was there damage, do people need help, and it was really the first sort of seismic instrumentation. The next seismometer wouldn't really come about until the 19th century. So in the late 1800s, there was a really bad earthquake off the coast of Lisbon, Portugal. At the time in history, Lisbon was a really important port. It was completely devastated by the earthquake. So in addition to the ground shaking, there was a tsunami and then there was a devastating fire. So as a result of this, and because we were in sort of the age of enlightenment, there was an idea of, okay, why don't we start studying earthquakes so that we can see if maybe we can predict them or if we can mitigate against damage or what can we do to make sure that we don't have more cities destroyed. So we started to come up with instrumentation. And this is really the first sort of seismometers that we think of in a modern sense. And they were dispersed around different places on the globes, but they acted almost more like a single individual stations rather than as a global network that we tend to think of today. Um, so when we talk about seismology, there's sort of two main sort of categories that we talk about, and one of them is seismicity. So this is the where, when, and why are events happening. So first of all, I would not be a good seismologist if I didn't do a lecture and ask who here has felt an earthquake. Okay. Oh, actually, most of you. All right. Who has felt an earthquake not in California? Okay, still a decent number. I always like to see just out of curiosity. So I shall note from the map, and I should mention these are magnitude 4 and above earthquakes that happened last calendar year. So you'll see the largest ones were 7.8, 7.7. The size of the circle is basically how big the earthquake was. So what you'll notice is they tend to form along these lines and patterns here, like so down the Mid-Atlantic Ridge, along the Pacific Ring of Fire. And this is because Earth is divided up into tectonics and plate tectonics. So because of plate tectonics, the earthquakes are more likely to occur at their boundaries. So there's actually red lines here of where those plate boundaries are, but there's so many earthquakes, it's actually quite hard to see. What you might also notice is that the smaller earthquakes tend to happen along the Mid-Atlantic Ridge where you have spreading sites. The bigger events tend to happen along these subduction zones where two plates come together. And this was actually really important for seismology and the understanding of plate tectonics. Plate tectonics as a theory is not that old. It was kind of came about in the 1950s and 60s. And seismology was one of the really key pieces of evidence for it because of the location of these earthquakes. You can actually see like the boundaries of these plates from the location of these earthquakes. Of course, we also have earthquakes that don't occur along the plate boundary. So this is the continental US. These are all magnitudes greater than 2.5. So again, not surprising, California is covered in quite a bit number of earthquakes. But then you'll also see regions like in Oklahoma that have quite a bit number of earthquakes. Most of those earthquakes are from induced seismicity. So when you do fracking and you have wastewater, when you pump that wastewater back down into the earth, it tends to generate earthquakes. You also get earthquakes around the Memphis area. This is the New Madrid fault zone. If you're eagle-eyed, you might notice there's this earthquake here that happened really close to Tucson. This was in September of 2023. It was like about a magnitude 4, I think. It happened in the early morning hours. So if anyone happened to feel shaking last year, you probably felt that earthquake. There's also these diamond shapes here. Those are for mining explosions. So when we go and we mine for minerals and we, create explosions, those get registered as events. Not pictured here was the Taylor Swift concert that also generated some seismic activity when she performed in Seattle. The Seahawks are also known to regularly induce seismicity in the Seattle area. So this just goes to show you that in addition to sort of naturally occurring events, humans do also create some seismic events. So we can also have events from, things like explosions, but also like rock falls, avalanches, where we have glaciers, the ice will crack. So we can get ice quakes, which are really fun and interesting to study. So with this seismicity, what we can then do is use it to look inside of Earth as well. So when a seismic event occurs, it releases a bunch of energy and they propagate out as seismic waves. And there's different kinds. So I should mention seismologists were not exactly original when it comes to naming things. So for waves that travel through the interior of a body, we call those body waves. If these seismic waves only travel along the surface of a body, we call them surface waves. It makes it a little bit easier to study. So for body waves, they can be either compressional or they can be shear, depending on their directionality. The P wave not only gets its name from like compression, but also primary, as it's the first arriving wave. S wave is for both shear and secondary. Again, we're very original in our naming. You can also get these things called normal modes, which is basically when the earth rings like a bell. This tends to only happen for really big earthquakes, though. So as I mentioned, after the Lisbon earthquake, we wanted to begin to study seismology in different ways. So we started to put out seismic stations. And we realized we can use this not just to look at hazards, but also look down deep into Earth as well. So in the early 1900s, scientists were able to confirm that we do have a core. You might notice there's not an inner core here yet because we didn't quite know about it. But basically, we were able to look at how these different seismic phases move out over time and distance and map them out and realize that there was something blocking seismic waves and something that was bending them. The inner core was actually discovered by a woman, Inga Lehman. She actually lived to be almost 100 years old, so she actually died almost fairly recently. And when she discovered the inner core, she gave her paper a somewhat interesting name. So in modern times, if you made a big discovery, like discovering an entire layer of the Earth, you'd probably come up with like a catchy title like Discovery of the Inner Core. She named it after the seismic phase, so she called it P prime. So the entire title of her paper is 2 characters long, which when I was a grad student and I was trying to read up on previous, seismology techniques and methods, I kept trying to find this paper and I was Googling things like inner core discovery and I could not find it. And eventually my advisor had to like save me and be like, no, it's this paper that has a completely seemingly random name. So thankfully we've gotten a little bit better at marketing, I think. So when, in addition to sort of the rough sketch of what Earth looks like, we now have a much better idea because now we have hundreds of stations that get deployed. We record thousands of events every year, so we have tons of data to work with. So we can get a really good idea of what the Earth looks like. And it's not too dissimilar from, like, say, a sonogram. So this is actually my daughter. So, when you go in for this, they bounce waves off and you can see things like, her head and her sucking her thumb. And just like seismology, we can get a sense of what's going on in the interior without necessarily having to go down thousands of kilometers. So, for example, we can see slabs that when you have 2 plates collide and one goes underneath another, you can see that slab get pushed down, basically down to the core boundary. We also noted these features here. They're called large low shear velocity provinces, or LLSVPs. We believe they're actually responsible for hotspots. So things like Hawaii, Yellowstone have these sort of telltale plume-like structures beneath them. So seismology not only was able to sort of help us with plate tectonics by figuring out, where those plate boundaries are from earthquake locations, but they're also able to help us figure out what is going on beneath our feet and within the Earth itself. So why do we get volcanoes not just at the Ring of Fire, but why do we get them in, Montana? Or, why do we have the Hawaiian Islands, even though they're in the middle of the Pacific Plate? So seismology has been really, really critical to the understanding of Earth and has really revolutionized geology as a science. So it makes sense that when we started to leave Earth and want to study other planetary bodies, that we would bring seismology with us. So this brings us to Apollo. Apollo was during the space race, the mission to head to the moon and to begin to explore it and to put Americans on the surface of the moon. So all of the landed missions from Apollo 11 through 17 carried seismic instrumentation. So when Buzz Aldrin and Neil Armstrong first landed on the moon, they brought a seismometer with them. So Apollo 12 through 17 were able to create a seismic network, notably not Apollo 13. If you don't know why, watch the Tom Hanks movie. It explains why the seismometer did not quite make it, along with some other things. But they were able to go from when we first landed in 1969 out to 1977. And the reason they actually stopped recording was not because they broke down or the batteries weren't working. It was purely budgetary. They got shut down because the NASA budget kind of dipped after Apollo. So they could have, in theory, kept recording for several more years. And during the Apollo experiments, they did both what we call active and passive seismology. So passive seismology is when you basically chill out and let the earthquakes come to you. So whenever there's a natural event, it happens in like the continuous data. An active experiment is when you're generating the earthquakes. So for Apollo, this was when the lunar modules took the astronauts off the surface of the moon. So we were able to record the rocket. When different stages of the rocket would crash back down to the moon, those are considered active experiments. We also had explosives that were an active source experiment. And these are really useful because you know exactly when and where they're occurring, which allows you to do a lot of science and figure out near surface internal structure and how fast your seismic waves move, which then helps you better locate the passive events that you do see. So there were a lot of key findings from Apollo that were really important. One of them is the moon is differentiated. So much like Earth, it does have a crust, mantle, and core. It's still a bit debated whether or not there is an inner core to the moon or if there is a partial melt layer around the outer core. Additionally, there were a couple of different events that were recorded. Most common is deep moonquakes. So as the name suggests, because again, seismologists are super original, these are moonquakes that happen deep within the moon. These are caused by tides. So as the moon creates tides on Earth, when you go out to the ocean, we create tides on the moon, except because the Earth is so much bigger, we basically are generating moonquakes. Additionally, we were able to look at things like the impact rate by recording the impacts that we were seeing with the seismometers. We were able to record shallow events as well, but notably the moon does not have plate tectonics. In fact, the Earth is the only body that has confirmed plate tectonics in the solar system, which is something that's kind of interesting and things that we are going to want to study. So basically, the moon gets its seismicity from a couple of different sources. So those shallow moonquakes, which are seen here, basically, as the moon gets older, it cools, and as it cools, it shrinks. If you kind of imagine, if you've ever had like an orange or like a grape that maybe got a little past its prime, you'll notice it's kind of wrinkly. The same thing happens on the moon. So we get these wrinkle ridges, and when they form, they end up generating things like these moonquakes. As I mentioned, you get tides that end up creating these deep moonquakes, which I'll come back to in a quick second. The impacts you get as well. So we recorded quite a number of them. And then there's thermal moonquakes. So as the name suggests, these are caused by thermal changes. The moon does not have an atmosphere. So as it goes from day to night, you get these really rapid temperature changes, and they cause cracking in the near surface. And things like the lunar module that were left behind, they also experience those same temperature swings, and they also experience sort of cracking and creaking, which generate these thermal events. So back to those deep moonquakes. So you might be wondering why I chose such like a low quality image and why it's so blocky and not as clean and pretty as the other ones. That's what they actually look like. So Apollo was great, but it definitely had some limitations. One of them is that the data quality is not great. So here's another example of a single seismogram for that deep moonquake. Here's what happens when you add 53 of them together. They start to look a little bit cleaner. The reason for this, one is that they were 8-bit as opposed to the modern day 24-bit. So for anyone that plays video games, imagine playing Mario back like in the 80s or, the old school Super Nintendo Mario versus modern day Mario, where you're able to see like facial expressions on him. That's kind of the same thing for seismometers. So we're going from that sort of low resolution to much higher resolution in modern day. There were also issues with timing and the clocks that were involved, as well as how often these samples were occurring. So with modern day, that's not good. With modern day seismometers, they're able to take many samples per second. We're basically limited by how much data we want to grab down at a given time. Apollo did not have nearly as high of a sampling rate, so that's why you sort of end up with this very blocky nature. And it makes it very difficult to do seismology when you have this sort of blocky nature because it's hard to identify when exactly is your P wave arriving, when exactly is your S wave arriving, which can make it difficult to do look at things like internal structure or things of that nature. So for that reason, and a couple of others, we're heading back to the moon. Out of curiosity, has anyone here heard of Artemis prior to me talking about this? Oh, okay, a good number. Yay. Um, in Greek mythology, Artemis is the twin sister to Apollo. So I think it's rather fitting that the new era is Artemis. There is quite a lot of thought and detail that actually went into the logo, and I'm not going to walk through everything. But essentially, Artemis is going to be our generation's Apollo missions. Sort of tied in with Artemis as well is CLIPS Prism. So that's Commercial Lunar Payload Services. I honestly forget what PRISM stands for. It's quite long. They came up with the acronym first and then tried to fit it. NASA has a tendency to do that. But basically, this is a new opportunity where private companies can build these landers and get us to the moon, and then we supply the instruments. And the reason I bring this up is because for one of them that will be launching in 2026, it's going to contain a seismometer. It's called the Farside Seismic Suite. It's going to be using essentially flight spares from the InSight mission to Mars. So it will be heading to Schrodinger crater, which is down near the south pole of the moon. So it will be able to also start to build a new seismic catalog of the moon. And these CLIPS missions happen roughly once a year. There's been a couple to go already with, how shall I say, limited success. Some did not make it. Some had harder landings, and some landed and then fell over. But that's sort of the point of these CLIPS prisms is they're not super expensive in terms of NASA terms. And we expect them to not necessarily succeed every time, but we want to give the commercial sector an opportunity to learn from mistakes and build up opportunities for them. So in addition to Artemis really focusing on the moon, one of the newer aspects is also NASA's push for moon to Mars. So the idea is that as we go to the moon, we can learn things that we can then apply to Mars. So how do we build habitats? How do we sustain humans on the surface of a planetary body with limited oxygen? How do we deal with things like space radiation? So a lot of the goals for Artemis can easily be applied to goals for Mars. So hopefully in the coming decades, we'll not just see people return to the moon, but we might finally see humans walk on the surface of Mars. Somewhat unlike Apollo, where there was a space race between us and the Soviet Union, Artemis is a bit more worldly. There are what we call the Artemis Accords. These are all the countries that have signed them to date. And really what the Artemis Accords are going for, I've outlined some of the goals here. It's a more peaceful, not military approach to planetary exploration and science. So there's really a push for peaceful exploration, um, the openness of scientific data. So there'll be like a brief embargo period when we collect our scientific data, but eventually it will be open to everyone. So anyone in this room can go and access the seismic data that we'll be recording. Um, Scientists all over the world will have access to it. So we'll really open up science discovery. There's also pushes for things like emergency assistance. So if something bad happens, it's not just only on the USA to go and potentially rescue astronauts. Um, it can be a more global affair. And really a deconfliction of space activities and space resources is another like big push for it as well. So Artemis, as I mentioned, is basically the equivalent of Apollo. So Artemis 1 already launched. That was essentially equivalent to Apollo 10. So it went around the moon. Artemis 2 will be crewed flight, and that will be basically repeating Artemis 1, but with people on it. That one is due to take flight next year. And then Artemis 3 is going to be the first time we put humans on the moon in roughly 50 years. This time we're also bringing a woman, which is really exciting. It's also going to not necessarily be people with a military background. In the early days of NASA, the astronauts were all essentially Navy test pilots. Nowadays, we have folks that have engineering backgrounds and science backgrounds. So it's not just people who are used to being put in very dangerous situations. So we're also hoping to make it a little bit safer as well. And when we head back, we're going to be exploring the south pole of the moon. So I should have mentioned this, but when Apollo landed on the moon, they basically stayed within 30 degrees of the equator and they were all on the near side. This is because it's easier to land near the equator and it's easier to have constant communications with Earth, which you can only do on the near side of the moon. So since we were sending humans there, we wanted to make it, as safe as possible and not take on too many challenges. But now we're going to push the envelope a little bit and head towards the South Pole of the moon. There's a couple of reasons we're really interested in the South Pole. One is that we think that there could be ice deposits, which would be really useful for us. So we can turn that ice into water, which, humans kind of need to live. There's also the possibility that we can turn it into things like fuel and other resources for us. So there are a couple of different potential landing sites. We really won't know where we're headed until very close to launch. But all of them are in this Shackleton region. And for reference, Earth would be pointing down this way. Artemis has quite a few different science goals that it wants to achieve. So Apollo laid a really great foundation for what we know about the moon, but it left a lot of unanswered questions. In particular, because we only landed on the near side of the moon, we don't really know a lot about what's going on in the polar regions and what's going on the far side. If you've ever looked at a map of the moon, you'll notice that the near side and the far side are actually quite different. And we're not really sure how deep does that extend. Is it purely surface related and superficial, or does it actually go down to the core mantle boundary? Those deep moonquakes that I was talking about, we didn't observe them on the far side. It's possible that that's just because we were only located on the near side and we couldn't see them because they were essentially in our blind spot. Or it could be because they don't occur on the far side. So that's going to be one of the really big science questions that we hope to answer. So these are the different science goals that were laid out by the Artemis Science Definition Team. And these are the ones that a seismometer can potentially help answer. So things like understanding planetary processes. So we know that the moon does not have plate tectonics, but what tectonic regime does it have? Are there signs of volcanism or dynamics within the lunar mantle? What is the current impact rate? How active is the moon? How can we use the modern impact rate to figure out what was the impact history like? Things like the late heavy bombardment, things of that nature. And then also, again, this ties into the Moon to Mars objective is how do we investigate and mitigate exploration risks? So when I showed that map of the US earlier, You could see there are some states like California where there's a lot of seismic activity. They have certain building codes to make sure that their buildings are less prone to earthquake damage. Places on the East Coast, they don't really get that many earthquakes. So they're more worried about things like how do we stand up against hurricanes, blizzards, different sort of natural hazards. So when we go to the moon, we need to know, is there a similar situation where there are areas of the moon that are more active than others? How strong are the moon quakes? Could they be as damaging as a large, California type earthquake that we think of? Or is it going to be more like the East Coast where, I don't know if you guys heard, but not too long ago, there was an earthquake in New Jersey and a lot of people were freaking out because New York, felt some shaking. I'd like to remind people New Jersey is a state. People live there. You care about those folks as well. I say that as someone who was born and raised in New Jersey. But my point being is their shaking there wasn't as strong, but because it rarely happens, it made all big news and headlines. So is that sort of what we're going to expect on the moon, where these events are rare? They can be big, but because they don't happen super often, we don't necessarily need to worry about them as much as, if we lived in Alaska or California. So that brings me to LEMS. LEMS is the Lunar Environmental Monitoring Station. And it has a couple of key science goals. So looking at the moon seismicity is one of them. So how can we better detect those deep moonquakes, shallow quakes, thermal moonquakes? What can we learn about the moon's internal structure? So can we finally answer, is there a lunar inner core? Is there a partial melt layer? Is the far side like the near side, or is there a weird dichotomy going on? And then assess the local and global seismic hazards. So since we are really interested in the South Pole for exploration, we want to see, is there heightened seismic risk there? Do we need to worry about this if we have a more permanent presence on the moon? So in preparation for SeisLEMS, seismology at LPL has going on for quite a number of years. So I actually first got involved when I was in graduate school back in 2017, where we were testing out seismometers. At that time, we were interested in ocean world exploration. So we were looking at seismometers in Alaska and in Greenland to see how they can record different types of events through ice and snow layers. So a slight brief aside, so that's me up there completely covered in Arctic gear. About 3 months before that photo was taken, I was at a conference where we were talking about field seismology. And I was saying, well, I'm a planetary scientist. I'm never going to be able to go to my field site because, they're all far away. And then I defended my thesis where I was talking about what I was going to do for the next 3 years of my graduate school. And basically, the too long didn't read version is I was going to spend the next 3 years in a nice climate controlled computer lab doing simulations. And then right after that happened, my advisor came to me and he goes, oh, we got a grant funded and it's to look at seismometers for planetary exploration. He says, do you want to get involved? And I was like, absolutely. This sounds great. He goes, cool. You're going to be going to Alaska next month. You need to go buy a parka. So it ended up working out fairly well for me because long series of events led to me being here. But just for anyone that's young, keep your options open because you never know how your life might change, and also ask questions before you agree to do things. Otherwise, you end up in Alaska and in Greenland for a month living on ice. So just to wrap back to this, Silicon Audio and University of Arizona began a partnership about 10 years ago to start developing planetary seismometers. So through different grants and field excursions, we were able to basically take their commercially available seismometer and make it ready for flight. So when the Artemis deployed instruments call came out, we were basically ready to go. So we worked with our PI, who's out of University of Maryland, Baltimore County, and Goddard Space Flight Center. And we were selected as one of the instruments that the Artemis 3 astronauts are going to be deployed. So for the first time in 50 years, when the astronauts return to the moon, they are once again going to bring seismometers, and those seismometers are going to be coming from Arizona, which is, yeah, Arizona pride. So we are basically acting as the suppliers for them, and we are also on the science team. So as we get data back, we'll also be looking at the data and start to answer some of those seismic questions. So in order to get there, we're going to have astronauts deploy us into the lunar ground. So when Apollo went, they put the seismometers basically just at the surface. Seismometers like to be buried. They're kind of like moles. The deeper you can get them, the better they tend to work. This is because the better that they're coupled to the ground, the better that they can record the shaking. Um, an issue with Apollo was that the lunar surface is a very fine material. And because there's no wind or rivers or water, there's no erosion really at the surface of the moon. So all of those fine grains are really rough and have very like sharp edges. And what ends up happening is that top layer of the moon is very dusty and it creates sort of scattering effects, which are not great for seismometers. It makes it hard to identify when those different seismic waves are coming in. So what we're going to try to do to mitigate that is we're going to be using a drive tube to have our astronaut basically put us into the ground. So we're going to be buried a couple of centimeters down. And then our slightly larger instrument will be put in a trench and covered to help, again, mitigate against those effects of the regolith. The other advantage of being buried is that you're not going to have as huge of temperature swings. So when you're at the surface, when you go from day to night, the temperature will swing quite a bit. But when you're buried, you don't have that same sort of temperature swings, which is really good from an engineering point of view because it means we don't have to test down to, minus 200 degrees C. We can, go to only minus 50 or minus 80 degrees C. So it makes our instrument a little bit happier. It makes it so we don't have to send heaters and extra things with us. So one of the things we hope to do is to look at lunar seismicity again. So our instruments are quite sensitive. I know this plot is a bit complicated. Basically, the way to read it is the lower you go, the better your instrument is. So Apollo, the geophone is this green line, and then their short period seismometer is this gray line. So basically, we beat both of them. So we're sending both a short period and a more broadband instrument. So for the short period, it likes higher frequencies, which is why it dips down low here. For our broadband, it likes longer periods, which is why it works better in the smaller frequency ranges. But we should be able to see things like near surface structure, cracking events, impacts both from natural and artificial sources, body waves from those tidally induced deep moonquakes. We might also maybe be able to see smaller like impacts as well as potentially free oscillations, which is quite exciting. And for anyone that was very or closely followed the InSight mission, our short period seismometer performs about the same as the InSight short period seismometer. So some of the events we hope to see are things like those deep moonquakes, impacts, shallow events, and those thermal events. So when it comes to thermal events, you can have two different kinds. Ones that happen from basically the regolith cracking, and then events from lunar module or like man-made objects being left behind. And they actually have different signatures. So those lunar thermal quakes that are generated by like things like the lunar module, they actually have higher amplitudes and higher frequency ranges compared to those more natural events. So we can look at things both in time series and then also like in frequency content. So you can kind of think about it as if you're listening to a song. So deep moonquakes, they have relatively low amplitude and then they have very low frequency content. So you can kind of think of them as like your bass. Shallow and impacts, they have a little bit higher frequency content, a bit higher amplitudes, and they also tend to last pretty long. So this is 3,000 seconds, 2,000 seconds. And then your thermal moonquakes, you can kind of think of them as more like a squeaky pop noise. So they have fairly high amplitudes, but they're very short in duration and they're very high frequency. So if you were to listen to like the symphony of the moon, you could pick out these different events based on the different tones or notes that they generate. I should mention seismic waves are not all that different from audio. So you can actually turn these signals into audio and listen to them. So you can hear the moon cracking and creaking and what that sounds like. And we've also have done that for Insight, I should mention. So how many events do we think we might get? It kind of depends on how long we're actually deployed for. Initially, we should be able to go for at least 3 months, but we can survive for at least 2 years. So it essentially will come down to how much money does NASA want to give us. So call your congressmen and senators and tell them to keep funding us. Because the longer that we're deployed, the more events we can detect. So if we're on the moon for about 3 months, we should be able to get tens, maybe hundreds of deep moonquakes. But if we're there for 2 years, we can get over 1,000. With impacts, same thing. We might get a handful, tens of impact events. But if we're there for a few years, that goes up to a couple hundred. Shallow moonquakes are a little bit trickier because they are more rare. It's hard to say exactly how many we're going to get. It's kind of like saying how many magnitude 7 events are we going to get in a given Earth year? We know we're probably going to get a handful, but we don't know where they're going to occur and when exactly they're going to occur. So with these seismic events, we can use it to figure out what does the interior structure of the moon look like. So for things like where is that basin ejecta? So when you have an impact event, it's going to throw material up into the air. So we can see how much of that upper layer is basically from those different impacts. How long does it take until you get down to unfractured crust? So essentially, like, where is the bedrock? How much of this is loose soil compared to solid rock? And then how deep is that mantle? So basically, how thick is your crust? And we can do this by looking at the seismic waves that bounce off these different interfaces and how they basically align up in time. So we can essentially use time equals velocity times distance, distance over velocity, to back out the depths of these different layers by knowing the velocity of the moon and how long these seismic waves take to arrive. We can do the same thing for the deep interior. So when you have an event like a deep moonquake, you'll have seismic waves that bounce off these different interfaces. So we can see if that partial melt layer is there, or if there's no reflection, maybe there's only that bounce off the outer core. Same thing with the inner core. If that layer isn't there, you're not going to see this bounce there. So this is what essentially they would look like on a different seismogram. So SCS would be a shear wave that bounces off the core. Anything with an I would indicate it passes through the inner core. So if there's no inner core, you're not going to see these seismic waves on your seismogram. So that's how we'll be able to figure out what's going on deep within the moon. And this is not too different from what we did with Insight. So I was part of a team that was able to figure out how big the core is. One of my favorite random facts is the author of this paper is Simon Stoller. His initials happen to be SCS, which is the name of the seismic phase that you use to find the core. So I like to joke that that's why he got first authorship. It's because it just aligned too well. But he actually is a really great scientist, so he deserve it. But basically, you can do different filtering processes and not too different from how you might filter or play with audio data to get different sound qualities. We can do the same thing with seismic waves to sort of tune into those core reflecting waves and make them stand out of the background, which is how we figured out exactly how big the Martian core is. And we'll be doing similar techniques to figure out the lunar interior structure as well. And lastly, the big science goal that we're going to be looking at is those seismic hazards. So the different landing zones are pictured here in the blue areas. The green stars are where previous events from Apollo were recorded. And then the yellow is all different places where seismic events are likely to occur. So what we can do is model what a potential event might look like. And it turns out they can be quite strong. In an earthquake, we tend to think of things as acceleration and gravity. So if you have an event where the ground shaking is as strong as gravity, you will feel weightless for a few seconds when that occurs. So to give you an idea, that lunar mark is this red line here. So a nearby event could cause ground shaking well above that lunar gravity. Uh, it turns out that seismic hazards might actually be something that we do want to really think about. Because even though these events are not going to be happening that often, if you happen to be close to where they occur, they could actually cause pretty moderate, severe shaking. So this is something we definitely want to think about as we head back to the moon and we're building habitats, is we might want to make something that could stand up to some seismic shaking. You know, is this going to be as dangerous as, say, the lack of atmosphere and air? Probably not. Um, but it's also not something that you're probably just going to want to brush off. But figuring out exactly how often these bigger events might occur is going to be one of the key goals of the LEMS mission. So what we're going to be working on over the next 2 years as we prepare for launch. Currently, we're slated to fly in September 2026. So right now we're building engineering and training models. So it's really fun. Basically, every day we get like nice little photos of the seismometer slowly getting built over time. They're going to be coming to Arizona to test in our nice new Applied Research Building, which is one of the newer buildings on Speedway. So we're going to be able to do shaking and vibrational testing. This is to see if they'll survive launch on the HLS. We're also going to be testing them to see how they perform over the temperature ranges and lack of atmosphere to make sure they'll be able to survive the lunar surface. We're going to be using some of our instruments to train the astronauts. So how do you go and deploy? How do you turn the seismometers on? How do you make sure they're working? Because we don't want to take all the money that we've invested in building them only to have them not get installed correctly. I should mention that during the Apollo era, there was one astronaut who was a geologist. And when he was carrying one of the instruments, he tripped. And it happened to be one of the seismic instruments. So there is, unfortunately, a history of seismometers getting dropped on the moon. There is a GIF of it on the internet if you want to go. It is quite funny. He's fine. But yeah, so eventually we will be delivering those flight sensors. And yeah, in September 2026, we will hopefully be launching out of Cape Canaveral and heading back to the moon. So with that, I'm happy to take any questions.
Well, thank you, Angela, for that great talk. Anybody online, there's a box you can type questions in, and we'll be taking questions from online. And let's say in the back, did I see somebody yeah, go ahead, in the black shirt.
Do tidal forces or libration affect how you make your seismic measurements?
Yeah, so the tides will be creating moonquakes, which are events that we'll be able to like record and see. Yeah, the surface will be moving slightly from that, and that's essentially what we're going to be measuring. Yeah. But because the main tidal forces happen deep down within the moon, they're relatively weak signals compared to, say, an event happening at the surface.
Mm-hmm. Yep. Okay, for doing the mapping down toward the core, et cetera, what size of a slice are you hoping to get with your limited seismometer stations that you've got?
That's going to depend a lot about where the sources are actually occurring. So if we get them from like a wide range, we can actually get a pretty good slice. So I'm actually going to go back to an earlier image. So from Apollo, let me make this full screen.
Could I suggest you repeat the question for the people online because they won't hear the question?
Oh, okay. Yeah, thank you. So she asked, how big of a slice do we think we can see of the deep interior of the moon? So for Apollo, and this is not full screen, sorry. So for Apollo, the stations were, so here was 15. Here were some of the other seismic stations that got cut off a little bit. So we were able to see quite a big slice of the moon, even though they were located all fairly close to one another. So we expect somewhat similar coverage. So if we're located down near the South Pole, we will be able to see this previously unexplored region. So the North Pole area will be basically hidden to us. But if there is an event that happens like in the near surface that is quite large, it will still create like surface waves that will travel along the outside of the moon, and we'll see some deflection. So we won't necessarily miss everything. But if there's events like these moonquakes, those are going to be trickier for us to see just because the core is blocking a lot of them.
Follow-up question. Are there any other active seismometers on the moon right now?
Not right now.
Okay.
So when the Indian Space Agency landed last year, there was a geophone, which is a type of seismometer that's not quite as sensitive. So that was like the green line that I showed in an earlier plot. So it recorded only for a very brief moment in time. There has not been a paper out yet, to my knowledge, but they did an initial press release that they do think they recorded at least one event. So we're hoping that once that paper comes out, we can see exactly what they recorded. There will be the Farside Seismic Suite that will launch hopefully in early 2026. So there is the potential we could overlap a little bit in time. That's also heading towards the South Pole area. And then the Chinese Space Agency is also hoping to include seismic instrumentation on Chang'e 7, I believe. And I think that's launching in 2027. I could be wrong.
Okay, thank you.
Yeah.
I have a question. You know, one of the myths, or it's a true story of LPL, is that to help the seismometers in the later Apollo missions, they dropped upper stages onto the moon to create artificial moonquakes. And Ewan Whitaker, whose portrait is out here, famously found where these craters were and located them. But is there any kind of similar idea of dropping things onto the moon to make moonquakes?
Yeah, so not specifically for us, it's just coincidentally also going to be happening. So when the astronauts do leave the surface of the moon, the newer rockets are likely going to be so powerful that we probably don't actually want to be turned on during that time. Because the ground shaking is going to be so severe that our seismometers are essentially going to like max out. We call it like clipping. So again, to make an audio analogy, it would blow the speakers. But yeah, there is a possibility that we might see debris or some stages coming down.
Amy, is there anything online questions?
No questions online right now.
Okay, thank you. Let's say in the green shirt. Yeah.
Is the current seismometer going to be of 3 axes?
Yes, so LEMS is going to be 2 seismometers, a short period, and a broadband instrument, and both are going to have 3 axes. So in total, it will be 6. Yeah, which is more than Farside Seismic Suite, I should add.
In the back.
Is there a way to measure the strength of moonquakes? Is there a magnitude scale for that?
Yeah, so we're gonna end up using the same magnitude scale that we do on Earth. So raise your hand if you've learned that earthquakes are measured on the Richter scale. Yeah, that's super wrong. That was true like 50 years ago. We have not used that since. The Richter scale only works if you use a very specific seismometer and you are only looking at Southern California. So that is always a pet peeve of mine in movies when they talk about the Richter scale, because we have not used that in a long time. Sorry, had to get that off my chest. So what we do is we call it either a moment magnitude scale. So we measure the seismic moment, which is basically just a function of how strong your rock is, the area that was affected, and how long your fault is. So the bigger the fault, the bigger the area affected, the bigger the earthquake. There's also some other ways that we can report them as like body magnitude, which is how strong your body waves are. They're all essentially linked to one another, but moment magnitude is typically the way that we think of it. So now when you hear the news say there was like a magnitude 7 event, that is the magnitude they are referring to, not the Richter scale.
Uh,
Do the silicon audio instruments work the same on any size body, or are they being customized specific to the moon?
The general physics works the same. There is some minor tweaks that we do. So for example, with the original ocean world applications, we had to make sure they could withstand very, very cold temperatures, like 90 degrees Kelvin cold. With the moon, we're more concerned about making sure their tilt is good. So with a lot of seismometers, you need to make sure that they're pretty level. So like InSight on Mars had to be within 0.5 degrees. Our seismometers can be tilted up to like 15 degrees. So that comes a little bit more in handy when you're doing a deployment like this and you're going to be buried so that you can withstand being, put in at a slight angle as opposed to directly vertical. But yeah, if you wanted to take like the instruments that we're sending to the moon and send them to Mars, it's not going to be like a complete like redesign. It might just be like, okay, now we need to take into effect that there's an atmosphere on Mars, so we want a wind and thermal shield. So it's little things like that.
okay, one last question.
Yeah.
Go ahead.
Is there any like competitors? I immediately think of like Elon Musk and SpaceX. Are they kind of doing something towards this as well? Or are they kind of just
So SpaceX is providing the human launch services, which is the rocket getting us there. So SpaceX is a rocket company. They don't necessarily do scientific instrumentation. So we would use them more as like a partner to get us there, rather than like compete with them over like the science build. Yeah, it's easier to think of them as something like a Lockheed Martin in some sense than like a science payload.
Oh. Okay, well, thank you so much, Angela, for a great talk. Let's thank her again.